So question 3 here for the 2009 scholarship paper. It's quite an exciting one to do with the trebuchet. We've got a little picture down here with the trebuchet. We've got acceleration due to gravity stated. And in case you've never seen or know what a trebuchet is, you haven't seen Lord of the Rings or anything like that, the trebuchet is a medieval weapon for hurling rocks and other things at fortifications. So very quickly, we've got the base, and it's on wheels, and this you can see that this beam here is going to pivot in that direction, and the rock is hurled away. You can see from up there. Now the counterweight has a large mass M, and your rock up here has a small mass, small m, which oh, there we go, it's mentioned from there in the sling. And the sling sort of rotates and moves around a little bit to flick the ball. I suppose you could flick a ball, but it's a small rock. Anyway, the lightweight beam indicates that the beam is going to be of negligible mass. So as we get down to the question, we're going to see that that's important. We have to state the energy changes that take place when the machine fires the rock. So the most obvious thing is that you've got gravitational potential energy, EP grav, from the initial big mass, and that is turning into kinetic energy for the big mass as it falls. But not only that, you're getting kinetic energy for the small mass as it moves, but you're also getting gravitational potential energy, EP grav, for the small mass M2. There's actually a few other ones going on, but that's the basic outline. You might like, if you consider the beam to be of a non-negligible mass, that is, its mass matters, then there's going to be rotational kinetic energy, EK rot. I haven't drawn that very well, but it's rotational kinetic energy in the beam. There's another source of where the energy can go to. And of course you would have friction and different things like that where you cause heat in the bearings and whatever is going on there. But the main things are gravitational potential energy from the large mass going to kinetic energy in the large mass as it falls, and kinetic energy in the small mass as it goes. And you'll have some gravitational potential energy at the point of release as well. Okay, you can explore those in more detail. Moving on. Assuming that the rock is released from ground level, show that the theoretical maximum range is this formula, r equals 2 big M over little m times by the height, where big M mass of the counterweight, small m mass of the rock being flung, and h is the height that the counterweight falls. If we quickly go up here, this is the height that it's talking about here. Okay, or the height above, well, the height that it falls, yes, so that's right. So how do we start this? Well, this is projectile motion, so it might help to draw a parabola, just for your thinking, and identify that this is the range. Okay, range. Remember, the horizontal velocity is constant, so VH, the horizontal velocity, is constant, and to find the range is your distance measurement, if you like. To find the range, we need the time of flight for that constant horizontal velocity. So if we were to do that, the range is equal to the horizontal velocity times by the time of flight, the total time of flight. Just preempting something, we usually, when we're trying to find the time of flight, we usually find the time to go half of the flight and then double it, because it's easier for us doing our calculations to find the time for half of the flight. And one of the things which will help us in that is that when we're dealing with the vertical velocity only, the vertical velocity at this point equals 0 at the apex of the flight. So that's going to be a useful bit of information. What else do we know and is useful for us? There's going to be an initial velocity at a particular angle. Now, this is for the theoretical maximum range, so we can make a good assumption about what that angle is going to be. And to get the maximum range, your angle theta is going to be 45 degrees. So that's important, that's very important. We can then take that initial velocity at the angle theta to find the initial horizontal and the initial vertical velocities, which are going to be useful later on. So VH is going to be V cos of theta. And interestingly enough, VV, the initial vertical velocity, is going to be V sine theta. And as I was saying, interestingly enough, those two should be equal and opposite, since you're dealing with equal and opposite. They should be equal, but in different directions, clearly, vertical and horizontal. Equal because sine of 45 is the same as cosine of 45, which is about 0.707. So that's just going to be helpful for us. If we then, let's carry on down, we then have our, go back to blue, our expression for our range slightly changing. It's going to be V for that initial times cosine of 45 degrees times by t. So we now need to come up with an expression for t and see where that's going to lead us. Okay, so remember, t is going to be 2 times the time for half the time of flight, and if we're considering the time of flight for the second half, you would have your initial vertical velocity as 0, which was the velocity at the top, and at the bottom your vertical component is going to be equal and opposite to that which it was at the start, so it's going to be V sine theta, but in a downward direction. Okay, acceleration is g still all the way through, and t is t. Or t is actually t half in this case. So the easiest equation to use is, I'm going to quickly change colour and draw that in the middle here, is Vf equals Vi plus A times t. Initial velocity, as we said, was 0, so we can ignore that term. Our final velocity we know is V sine theta, because V is that initial velocity and it's the component of that, which sine theta gives us. A is g, so that equals g times t. So we can see that t is going to be V sine theta over g, which means we can plug that into our equation down here and end up with V cos 45 degrees times by V sine theta, which is V sine 45 again, and we're dividing by g. So this is a very useful step. Putting that all together, we end up with V squared over g, and because we've got this sine 45 times cos 45, that's a number that we can actually deal with quite nicely. 0.707 times 0.707 equals 0.5, which is half. So we're going to store that up for a moment. We've got a range expression, and we're part of the way there. We now need to find out, because g is g, 0.5 is 0.5, we now need to find out an expression for v, or for v squared. And we can do that using the kinetic energy formula, because remember, kinetic energy equals half mv squared. But we also have the gravitational potential. Remember, that is going to be the kinetic energy of the small rock, so it's a small m, just to emphasize that. I made a mistake when I was practicing with this earlier. And the EP grav, which we initially start with, is big M G H. So those two equal each other, and we end up with half mv squared, small m, v squared equals big M G H. See, my mistake was I didn't deal with the large m and the small m, and I cancelled them out, and then I was wondering where I was getting mixed up. But I found out what I was doing. Anyway, rearranging this for v squared, we have v squared equals 2 large m over small m G H. And you can see where that large m over small m part comes from. Now, I have missed out something up here. what is it? It's a factor of 2 that I've missed. I'll just pause and think about it. Okay, I've forgotten one aspect here. Remember, our time of flight is actually twice half the time of flight, so there's actually another factor of 2 I've forgotten to include in here. So our range there is going to be 2 times, and nice enough, that's going to cancel out with our 0.5, so we're left with v squared over g. So as I said, we're looking for expression for v squared, and we've got that down here. So our range, let's write this out in full, equals v squared over g, but in this case our v squared is equal to 2 big M over m g h, and all of that divided by g, because that's the v squared section. So these two will cancel out, and we're left with our range equaling 2 large M over small m times by h, which is exactly what we're looking for above.